class. So every class is recorded. So class now is recorded.
And they'll get a G for good, F for fair, and S for serious. So I made a little chart. Okay. So first, the sample size. I thought the best way to do it was to write it out.
What's the question, Emma? Hold on. What's the question? What are we doing?
Can you see it? It's right here.
Yes. Yeah,
Okay.
read the questions. I know you read the settings, the setups you read. So what are we looking for? What's the question?
So first, the question's asking for the sample space of the experiment that I described. So the sample size is 6 because there's 6 possible combinations of insured or not insured, and then good, fair, serious. You could also do 2 times 3 because there's 2 in each of them. And then B says, let A be the event that the patient is in serious condition, specify the outcomes in A. So then it's either insured or not insured with the serious condition. And then C is let B be the event that the patient is uninsured, specify the outcomes in B. So if it's uninsured, it's going to be 0 and any condition. So good, fair, or serious. And then D says give all the outcomes in the event B to the C union A. So union means or. So I put all the opposite of what B was because it's supposed to be the corresponding elements.
Hold on, Emma.
Yeah.
B to the C, let's call it complement of B.
Okay, complement. So the complement is what's not in B, like what we don't see in B. So instead of the uninsured, it's the insured. And then it's the union of A, so we also have to put the A components. And one of them overlaps, which is 1S. So I didn't put 2 1S's, I just left as well.
Great.
Thank you.
Great. If anyone has any questions, just feel free to ask. All right. Okay, that's Emma. So with statistics, with probabilities, let's make sure we're using the right term. So complement of B of an event. Okay, let me give you grades. Whenever is ready, let's go ahead.
Can I see my screen now?
Yeah.
So this problem is from chapter 2:7. A bus departs from bus stop 16 with 20 passengers. The bus journey will end at the bus stop 20. Passenger can leave the bus at any stop, but no passenger can board. Work out the number of possibilities in A, the whole sample space. So there's 5 stations from 16 to 20. That implies 5 variables for total 20 people. And by 6.2, use this formula, we got 24, choose 4. And that's equivalent to 10,626. For the part B, the event that no passenger leaves at bus stop 16 or 18. So there would be total 3 stations. So it would be 22 choose 2. And we got 231. And for the part C, the event that half of the passenger leave by the bus stop 18. So before bus stop 18, there's 3 variables. So and there's half passengers. So we have 3. So the RB3 and the NB10. So we have 12 choose 2, and that's 66. And after the bus stop 18, we have 11 choose 1. Because after stop 18, we still have 10 people, and we have 2 more stations. So the R will be 2, and the N will be 10. And then apply to the formula, we got 11 choose 1. So 66 times 11, we have 726.
Well, this is a great question, but you are going over too fast. Can we go back a little bit?
Yeah.
Let me understand the question. So question 7 is a bus departs from bus stop 16 with 20 passengers. The bus's journey will end at bus stop 20. Passengers can leave the bus at any stop, but no passengers can board. So work out the number of possibilities in this. Okay. So the whole sample space, 5 stops. The whole sample space. Okay. How did you figure out the whole sample space?
First of all, there's 5 stations. That implies 5 variables. So there's station 1, 2, station 2, so and there's total 5, and there will be 20 people get off the bus. And apply to the 6.2 formula, will the n be 20, r be the 5, and that would be 20 plus 5 minus 1, and 5 minus 1. That would be 24, choose 4.
Okay, great. I see. So this basically will assume the 16, 17, 18, 19, 20 stops. Then you're treating each stop as variable x1, x2, x3, up to x5. And then the passengers, 20. But it says the bus's journey will end at bus stop 20. Passengers can leave the bus at any stop. Oh, okay. So that means that any variable can be 0.
Yeah.
x1, x2, right? Any variable can be 0, but it just adds up to be 20. So the whole sample space is basically how many terms in this? How many solutions for this?
That's 10,000.
So right, that's why you use the proposition 6.2 to say, okay, the 20 minus r equals 5, n equals 20, so 20 plus 5 minus 1. Then choose r minus 1, 5 minus 1, which is 24, choose 4, which is this many. Okay, that's the whole sample space. Okay, great. All right, so B, can you explain B again? B says the event that no passenger leaves the bus stop 16 or 18.
So we only go to 17, 19, and 20. So instead of 5 stations, we have three stations. So we have let n be 20 and r be 3. And the same formula, we got 22, choose 2.
Oh, that's smart thinking, because I was thinking about, okay, so we just exclude bus stop 16 and 18. All right, great. And C, the event.
Yeah, we have 2 parts.
Half of passengers leave by bus stop 18. Oh, at 18, half, okay.
So at the stop 18, there's only 10 people left. So before 18, there's 66 possible case. And after 18, there will...
How do we know it's exactly 10 then? What about the passengers already leave at 16 and 17? What leave at 17?
So because it say at the 18, there's only 10 left. So we have 3 stations before 18. So R will be 3. And since there left 10 people, so the N will be 10.
Okay, by stop. All right, by bus stop 18. That's why 16, 17, 18, you only consider these 3 variables adds up to be 10. Okay, now I understand. Right, that's what you're doing. Yes, n equals 10, r equals 3. Great.
And after 18, we have 11 case and multiply, we got 726.
Oh, hold on 1 second. So the C is asking the event that half of the passengers leave by bus stop 18. Okay, so the first half is out of 12, 10 plus 3 minus 1, choose 3 minus 1, which is 12, choosing 2, which is 66. Then you have to consider the rest of the 10, which is from 18, 19, 20, right?
Rest of 10 is from 19 and 20, yeah.
So 19. So that means 18. Oh, you only said 19, 20. So 2 R equals 2, and N equals to 10.
Mm-hmm.
10 plus 2 minus 1. Oh, I see. That's how you get 11. Oh, yes, right here.
And
Okay, great. Anyone has any questions? This question is great. Why is the 66? Oh, yeah, of course. The 66 possibilities, 11 possibilities by counting principle, we multiply them. 726. Great job. So this is a J. Great job. Anyone has any questions? Okay, Catherine is asking a question. Can you see it, J?
how'd you get 10? What do you mean 10?
Catherine, do you mean the rest of the 10?
Because it means a policy, because it says at the stop 18, there's only half left, and the half of 20 is 10.
Catherine, basically, he divided into 2 cases. So think about the bus stop 18, right? So by 18, half left. So that means the first 3 variables, 16, stop 16, we call x1, stop 17, we call x2, stop 18, we call x3, x1 plus x2 plus x3 equals to 10. So for those 10 people who left bus. And the rest of 10 will write for 19, well, maybe leave the bus on 19 and 20. So that's why R equals to 2 now, but you still have 10 people on bus. Does it make sense, Catherine?
Yeah, but how about the R that equals to 3? That is
R equals 3 because
That's
you
the
did 3 stops.
3 stops.
Yeah.
Oh, okay.
16, 17, 18. Because by bus 18, you have 10 people left the bus. So the previous one is 17, 16.
Oh, I see now.
Okay. Anyone else has any questions? This is a great test exam question. Thank you, Jin. You picked a very good question.
Thank you.
Next one. Okay, Catherine is up.
Okay, yeah. So I'm doing question 9. So in a school, 3/4 of students are involved in sports, half are involved in cultural activities, and 1/8 are involved in neither. Calculate the probability that a student is involved in. So like for part A, it's calculating either sports or in cultural activities. So based from the question, so we know that 1/8 of the students are involved in neither. So we must know that there's 7/8 students are involved in either sports or cultural activities. And then for part B,
So hold on. What's the answer for A?
for A,
Either,
7/8.
either sports. 7/8.
7/8.
Either sports or in cultural activities. That's given in the question, right?
Yes.
So
And then for part B, probability of like both sports and cultural activities. So we have we know like 3/4 of the students are involved in sports, so it's 3/4. And then we multiply students that are involved in cultural activities is 3/8 of the students. And then for
right here is
part
multiplication because it's an and. And
yes.
so A is or. Okay, great.
And for part C, cultural activities, but not sports. So we know that 1/2 of the students are in culture, and we know like because we know like we already know like 3/4 of them the students are in sports. So we know like 1/4 it's not in sports. So like we so the probability for cultural activities but not sports is 1/2 times 1/4 equals 1/8 of the students
Great.
that are not.
Great. So we see the complement. So the complement of 3/4 of students are in involved in sports. So not involved means the complement of these 3/4, which is 1/4. Good. You guys pick a good question. Anyone has any questions? All right. So the rest of you, when you show the a problem, go a little bit slower, so everybody knows what problem we are doing, which problem we're doing. Good job, guys. Who's next? I think this is a fun class. So you gotta, you gotta pick your own questions. So this is how.
Oh, I got a question for from chapter 2. ABCs takes turn flipping a coin. The first one gets heads, wins, and the symbol space is shown here. And it tells us to assume that A is the first flip, B is a second flip, and C is a third flip, and then it goes back to A again, B, C. It keeps going on. So for
Hold on one second. Hold on one second. Let me understand this notation. So as so 1, 0, 1. Oh, okay, I got it.
yeah,
No, hold on. 1, 0, 1, 0, 0, 1, what does this mean?
this is the first flip. 1 is the first flip, first one wins. 0, 1 is like the second flip.
Second
B.
one was.
And then C
But
is
we
the
only,
0, 0, 1.
but we only have A, B, C, right?
Yeah, so it like goes back to A again, B, C. It keeps going on for like A, B, C.
Got it.
And for the first one, it tells to like symbol space. It's the same like first one is A, second one is B. That's why I have like say already. For B, it tells A wins. The symbol space for A wins is the 1, and then going to 0, 0, 0, 1. It's a pattern, so you just add zeros to it to the front, and then like
You add a multiple of 3 zeros.
three zeros. For B, it's the same. You add like the symbol space for B. You start with 0, 2, then you add 3 zeros in the front. And for the third one, the symbol space of A or B complement, it's the same symbol space for A complement and B complement. So you only have like C in the symbol space left.
You're using De Morgan laws. It's the De Morgan laws. The complement of A union B is A complement intersection with B complement. Great. You're using, hold on one second.
Oh.
Can you put back?
Yeah. Pulling it back.
Yeah. So this is like a review for the previous class. So B define the following events in terms of S. S is a sample space, right? So A wins. Okay, that's why you have 1, 0, 0, 0, 1. Just keep adding multiples of zeros, multiples of 3, many zeros.
Yeah.
In front of them. B wins. B wins. B is the second 0, 1. Then A union B complement by De Morgan's law. That's A complement intersect B complement. So that A flips first, then B, then C, then A, and so on. A wins, okay. A wins only when B and C fails. B wins. B wins, which means A and C fails. So we have 0, 1. So adding multiples of 4 many zeros in front of 1. Right, by De Morgan's law. So complement of A intersection complement of B equals C. What do you mean by that? Why?
It says I think the question shows that the sample space of the
Okay.
sample space of this A union B complement. So what I got, it's like only C left in the sample space.
Right, A union B. A means A1s, B means B1s. The notation is very important.
Yeah.
So either A1 or B1. What's the complement of that? That's a C1s.
Yeah.
Yes. Okay, or you can think as De Morgan's law. So the notation you have is De Morgan's law, which is beautiful. Anyone has any questions? Okay, good job, Hao. Next one. Crystal, is Crystal here? Crystal registered later, I think. So for those of you haven't presented it yet, remember you need to present 10 times in total during the semester to earn your credits for presentation. Okay, all right, someone's work is up. Let me make this a little bit bigger. Yeah, go ahead, Tom, that's yours, right?
Okay. So we're showing that this summation is equal to 3 to the n. So it's very similar to the example on page 20, where they gave the combinatorial proof of the binomial theorem, where the basically the highlighted parts are kind of identical structure, where we have x is equal to 2 here, and for y we just set it to 1, because 1 to any power will give you the same result. So then from that equation, it is equal to x plus y to the n.
Tom, excuse me, Tom. So the question is 26, A and B part, right? To show those two equations.
Yeah.
Okay, so the rest is your solution, is a combinatorial proof of a binomial theorem. You're showing this one? You're showing...
So I'm showing that the
Oh, you're using it. Okay,
yeah,
you're using it. I see, okay. I got to pull this
equals
here.
3 to the n. So to get 3 to the n, we substitute x is equal to 2 and y is equal to 1. And then we get 2 plus 1 to the nth power, which then simplifies to 3 to the n. And then part B is the general form of that problem, where we have x to the k. And for the general form, we just have x plus 1 to the n.
Oh, B is simplifying. B is not the equation. B is to say simplify this, because the first one, the first equation is out of n choose k. K goes from 0 to n. 2 to the k's power equals to 3 to the n's power. You are saying, okay, let's use binomial theorem. So 3 raised by n is 2 plus 1 raised by n. So you just use up binomial theorem.
Yeah, where the y term is basically 1.
Right. So B is saying maybe use A to simplify this. X raised by k. X raised by k. Because you see 2 raised by k. 2 is 1 less than 3. Oh, okay. You say that's x plus 1 raised by k. I got it. That's x plus 1 raised by n. That's to use the first one. So once you establish A, so B is application. It's an example of A. Okay, anyone has any questions? This is beautiful. Thank you, Tom. Anyone has any questions? Great. Thank you. Oh, that's nice. All right, let's see. So Tom, Jay, Hall, Emma, Catherine. So everyone showed. So what about the rest of you? Any of you like to present any work? I think these five people showed us very good. All right, Raw wants to present the 10. All right, go ahead. Let me make you presenter, Raw.
Hello, can you hear me?
Yeah.
Okay. I was working on this while everyone's presenting because my questions got taken. So I need help on that split. But I've never presented on a tablet before, and I'm trying to see if it's
Do you
possible.
want to share your screen?
I'm on
You
a
go to
tablet,
you
and
go
I
to
can't
share.
like see an option. Yeah.
Do you see the share content arrow?
No.
On
You're
the
talking about
bottom.
on the bottom? No, I see.
Yeah.
I see mute video and raise your hand.
Oh, do you see attendees icon? You have 1, 2, 3, 4, 5 icons on the
Yeah,
bottom
I
right. Okay.
I see. Yeah.
The middle one is share content. If you click on it, it bring you to share blank whiteboard, or the second one, share applications / screen. Choose that one.
Share application says unavailable for me.
Oh no.
Yeah. Can I send
let
like a screenshot at some point in the class of my work? And like I'll explain it.
Yeah, anything you can show us.
Okay, I'll send you a screenshot in a few minutes. You can go on, or I can do it in like next class.
Well, you can use a whiteboard. If you think you can do whiteboard, requires a lot of writing.
If you're fine with that, I can do it. Yeah.
Do you see the whiteboard share content?
Yeah.
The first is a whiteboard. Okay.
Hey, can you see?
Yeah.
Can you see my writing?
Once you.
Okay.
Yeah.
All right. So I'm just gonna read the question out loud because I don't know if I can show it. I'm doing question 10.
Question 10. Let me find question 10 for you. I don't know which question 10. Question 10 is in how many
chapter
ways?
2. No, chapter 2, question 10, sorry.
Oh, where am I?
A restaurant manager was listing the types of items not ordered.
I'm still in chapter 1. Raw, you need to be better prepared next time.
All right. I've never done this before, so I just didn't know if it would work. It's my first time doing class from my tablet.
So this is based on your homework. You finish your homework, then just pick one of your homework to explain to us.
Yeah. So a restaurant manager lists items that were not ordered by a customer. The chance of them not ordering meat was 80%, which means the chance of them having meat was 20%.
Hold on one second. We need to show the people. Hold on one second. Let me share.
Right.
Let me share my screen with them first. Then you answer the question. So question 10 is this. A restaurant manager was listing the type of items not ordered by her clients, 80% of whom have meat. 10% do not have meat or dessert, and 25% do not have any dessert at all. What is the probability that a customer will have A, B, C? All right, so A is either meat. Let me see if I can copy paste to the whiteboard. A is either meat or dessert or both. It's or. B is meat but not dessert and complement. C, meat and dessert, so intersection. Let me see if it's possible. I don't think it's possible to paste. I don't know how to do that. Okay, anyway. All right, you go ahead. A, B, C, 3 parts.
All right. So the chance of them having meat was 20% because the chance of them, the problem said, not having meat was 80%. The chance of them having skipping dessert, they said, was 25%, which means the chance of them having dessert was 75%. And the chance of them having neither was, chance of them having neither was 10%. First question was, what are the chances they have either meat, dessert, or both? The combination of stuff you could have meat, you could have dessert, you could have both, you could have neither, is that will all add up to 1 because that's the entire sample set. So what it's asking for is, what was it? How do I undo this? Is there a way to undo this, Professor?
I don't think, let me see this. No, you could.
Okay. I don't just ignore it then.
Just ignore it.
So it's asking for meat, dessert, or both. The only other option is having neither. And since that makes up the entire sample set, it's 1 minus the probability they'll have neither, which is 1 minus 10%, which is 90% of 0.9. That's for A. For B, it's meat.
But not a dessert. Meat,
Yeah,
but
meat.
not the complement of dessert.
Yeah, I'm so sorry. I have no idea how this works. I'm going to do it up here. B, meat, but not dessert. What that's asking for is possibility of meat, but subtract from that the possibility that they will have, they'll have meat and dessert. So that would be the intersection. The way I did it was the intersection of meat and the not dessert.
Right, the complement of dessert.
Yeah. There might be an easy way to do this, but that's how I did it. And then this would be 20% minus possibility of 20%. The intersection is just multiplying the two probabilities, 25%. Then this equals 20% minus 5% equals 15%. I think looking back at it, I could have just done probability of meat times probability of dessert. That's the same number, but this is the way I did it.
Yeah, that's okay.
And
Good.
The last one is meat and dessert. I'm not sure if I did this right, but probability of meat and dessert. It would be the union, right? So it would be something like this.
No, it's and. And means intersection. Meat and.
Oh, intersection. So just PMD, right? Oh, I did the union. I did something like this. This is wrong.
What is it? What P of M is meat? Meat what plus?
Yeah, plus dessert. I think I did the intersection. I think I did the union. I mean, the intersection of meat and dessert, is it not just PMD?
Yeah, probability.
It's asking for meat and dessert.
Exactly.
Yeah.
Probability of meat and dessert.
So this part, right? This is this, right?
Probability of meat intersect the dessert. Yes.
Yeah, and then that would be 20 times 75%. But the reason I was confused is it this? The reason I was confused by this is because that's not what the textbook had.
It's not what?
It was not what the textbook said the answer was.
Oh, really?
Yeah, the textbook said 65%.
55%. Let's
65.
go back to
yeah.
65.
Yeah.
Because we want to find the probability of meat and dessert. Well, let's go back.
Yeah, the intersection. Yeah.
Meat. So only 20% have meat. Then dessert.
Yeah. It's a 75 chance that they'll order dessert. Yeah.
Or 75. Okay, 25. Right, 75 order dessert. So that should be 20 times 75, 15%.
Yeah, but the textbook says 65%, which is why I wasn't sure if I did it right. I don't know
The
if I'm missing something.
The textbook could have typos.
All right, so this is then this would be the way you do it normally then, right? Intersection,
Yeah,
just
I think you're
multiply
doing
that.
right. Yeah.
All right, so I have A, B, C. Okay. Sorry about that. I've never done this on a tablet. I've never gone to class or anything on tablet, so I didn't know how this would work.
So that means
I'll have better. Yeah,
okay,
I'll figure it out next time.
Right, because you have to do homework anyway. You have to pick 25
Yeah.
questions out of each chapter. So you just pick one from your homework. All right, but then this is good. Anyone has any questions?
Okay. Thank you. Sorry about that.
Okay, that's okay. So I think all of you pick up very good questions. You know, we just served for review, and yeah, I like it. Anyone else like to present? If not, let's go to let's go to our textbook. I think we're on section. I think we're here, right? We talk about some propositions. Yes, we have done this. So 2.4. Okay, so anytime anyone has any questions or comments, feel free to stop me at any moment. So some simple propositions. So we'll learn some propositions. Well, from previous class, we know this, right? So the sample space. So this is one of the axioms. Remember, I have 3 axioms for probability. Well, let's just review that because that's super important. Without the axioms, we won't be able to talk about probabilities. So probabilities stands up on those solid ground of 3 axioms. The first axiom is saying any probability of any event is in between of 0 and 1. Probability of the sample space is 1. Right? And probability of the union of all the events equals to summation of the probability of each event. So now with these axioms, with this solid ground, we can talk about probabilities. Some simple propositions. So probability of sample space equals to 1. Of course, use the probability of the union of complement and the event and event union its complement, right? Because what is event union its complement? That's a sample space. That's a sample space. So any event union its complement is a whole sample space. And this is union, so we can union, so that's probability of sum of probability of the event and the probability of its complement. So that's why a lot of times we find that a probability of an event using 100% minus probability of its complement, or vice versa. Probability of event complement equals 1 minus probability of the event, which is this. A lot of times we use this equation. So proposition 1. Proposition 2, if an event is included, right, in another event, that means the probability, the smaller event has to be less than or equal to probability of the bigger event. Well, if we want to go through the proof, that's the proof. And then we use E complement F to mean intersection. So this is E complement or complement of E, and F means complement of E intersect with F, with even F. Or maybe let's go over this proof. So if even E is included in even F, so F equals to even E union F intersect with the complement of E, of course, right? Because F intersect with the complement of E. is a something not in E, but in F. Then by proposition 4.1, property of F equals the probability of F equals the probability of complement of even E plus probability of the complement of even E intersect with F. And yeah, so this shows probability, you see. So probability of F equals the probability of E plus something. And this something is in between 0 and 1. So this shows this proof. Simple proof, right? Maybe appear on the exam. Proposition 4.3. Probability of even E union even F equals to probability of even E plus probability of even F subtract probability of their intersection. Because if it's an intersection of E and F, the probability will be inside here, counted here already, and also counted here already, because the event belongs to, the intersection of the two events belongs to this one and belongs to this one. So it's counted twice. So that's why we need to subtract once, right? So we use this, very often. The proof, well, let's go over the proof. So probability of E union F equals to probability of E union F intersect the complement of E, or which means the event E complement of E intersect with F means the event in F not in E, right? So equals the probability of even E plus probability of the intersection of F and complement of E. Then we can write event F as event E intersected with F, which means event in both of this. Then union event inside the intersection of the complement of E and F, of course, right? Make sure you understand the logic behind these statements. And then we can write, according to this and according to the propositions, we can write the probability of F equals the summation of the probability of those two intersections. And then we can substitute this one, probability of this intersection, into this. So that's, okay. So this one equals to this minus this, right? And of course, we can see this one because again, this probability of this event in between of 0 and 1. So of course, this one is. So we want to prove this one, right? We want to prove this one. Let's see. We should have more just. Okay. So let's see why this is proof that E union F. So this is so we start with this probability of E union F. So we finished by P of E, P of F. All right. So that's right. We substitute this one into here, right? So the proof should have read one more line. Because here we have those two. Now we substitute this one into this two. That completes the proof, right? So that's P of E plus P of F minus P of intersection, because this one is this one. All right, Q proof. So this thing, proposition 4.3, could also be improved by Venn diagrams. Right, this is by Venn diagram. Venn diagram is easier to see, right? Because if we have E union F, probability of E union F, we see the intersection belongs to E and also belongs to F. So when we talk about probabilities, this middle part being counted twice. That's why we need to subtract once. Let's see an example. If anyone has any question, feel free to stop me. So anyone has questions over those two propositions? We use this all the time, right? We use this all the time. Let's see this example. 4A. J is taking 2 books along on her holiday vacation with probability 0.5. She will like the first book. With probability 0.4. She will like the second book. And with probability 0.3, she will like both books. What is the probability that she like neither book? Right? She likes neither book. So let BI denote the event J likes books. So I equals the 1 or 2. Then the probability that she likes at least one of the books is probability of B1 union B2, right? The first book and second book, she like both. She like either one. The probability of she like, you know, one of those 2 books is probability of the first one plus probability of second one minus probability of the intersection of the first one and the second one. She likes both books, right? B1, B2 here means she likes both. What's the probability she likes both? 0.3. Probability she likes the first one is 0.5. She likes the second one 0.4. She likes both 0.3. So we just add 0.4 plus 0.5 minus 0.3, which is 0.6. Right, so this is a probability she likes, you know, one of these 2 books. The question is asking, what is the probability she likes neither book? Right, she likes none. So we're looking for the complement. So the complement, she likes none. So which means the intersection of the complement of first one and the complement of the second one. She doesn't like the first book. She doesn't like the second book. And which is by De Morgan's law. So this is the intersection of the complement of the first one and the complement of the second one. By De Morgan's law, that's B1 union B2, the complement of B1 union B2. Right? What's the complement? What's the probability of the complement of event? Is 1 minus the probability of that. So which is just 1 minus 0.6, we get 0.4. Anyone has any questions? Okay, so this is just so this is saying we may also calculate the probability that any one of the 3 events E, F, and G occurs. So let's see, if we want to find probability of the union of 3 events, that would be that we could do E union F, then union G. So basically we could union any of those 2, treat it as one event, right? We could treat E union F as one event. Then we're just treating this one as a probability of one event. And do this. And then for this one, we have that already. We have this. Then plus this part. Plus this part. So we simplify this. So what is this part? This part is E intersect with G, union F intersect with G. Right? We use the union of this. Well, what's the union of this? That would be probability of the first plus probability of the second minus the probability of the intersection. Well, with this minus sign already, so let's switch the positive to be negative and negative to be positive. And then we have probability of F, E, probability of G, minus the probability of intersection of EF, minus the probability of intersection of EG, minus probability of the intersection of FG, then, but the plus probability of the intersection of those 3 events. Why? Because in here we subtract once, we subtract twice, right? We subtract twice, we subtract 3 times. but this is the intersection of 3 events. So E, F, E, G. Oh, we subtract twice. You see, we can calculate this one and this one. So this is E intersected with F, E intersected with G, then F intersected with G, right? So that's why we need to add back once. See, another proposition. So this proposition, so basically, you know, depends on this. From 2 events to 3 events, we could see up to n events. Up to n events, we have this summation of all the events, probability of the events. That's this part. Then subtract probability of intersection of 2 events. That's this part. Then add back what it depends, right? That's why we have -1 raised by r plus 1. You can imagine we keep subtracting. Well, we would subtract probability of the intersection of 3 events, then add back 1, keep going this way. So in the end, it's -1 raised by r plus 1. Then add back -1 raised by n plus 1. Well, is this one proved? Okay. Let's not care about these proofs, all right, for us. If you are interested in this, if you want to learn more probability theory, so you need to go over these proofs, all right? Just for those ones who's interested in going to statistics area for your occupation or probability theories, you go over with this, but I'm not going to spend time on this proof. So for us, you know, it should be good enough to remember this, the union of 3 events, the union of 3 events. Okay, 2.5. Sample spaces having equally likely outcomes. So in many experiments, it is natural to assume that all outcomes in the sample space are equally likely to occur. That is, consider an experiment whose sample space S is a finite set. Says, you know, the sample space are 1, 2, 3, up to some, you know, finite n number. Then it's often natural to assume probability of getting 1 equals the probability of getting 2 equals the probability of getting any of the numbers in the sample space. So which means P of any, the choice of any member in the set equals 1 over n, because we have n members in the sample space. So probability of any event equals to the number of outcomes in E divided by number of outcomes in S, right? So, you know, probability is always a part of something over the whole thing. The number of outcomes in S is the whole possible events. A number of these interested events we call E, the number of the outcomes in this interested event, in this interest, in our interest, for our interest event. So number of outcomes of in E and over number of outcomes in S in the sample space. So that's the probability of the event. In words, if we assume that all outcomes of an experiment are equally likely to occur, then the probability of any event E equals to the proportion of outcomes in the sample space that are contained in E. Let's see examples 5, 8. If 2 dice are rolled, what is the probability that the sum of the upturned faces will equal 7? Right? So we'll land on which number? And the sum, we're tossing 2 dice at the same time. So we'll consider, adds up those 2 numbers to be 7. Well, we can make a list. And totally, we know 2 dice, because each one has 6 possible outcomes. So for 2, 6 times 6, so we have 36 possible outcomes. So the sample space of 36 members. So in the denominator, we have 36. But how many outcomes there? So the 2 numbers adds up to be 7. How many possible outcomes? Well, the first one could be 1, second one could be 6. So 1, 6. Well, first one is 2, second one is 5. First one is 3, second one is 4. Or switch those 3, right? So those are all possibilities for the first one to be 1, 2, 3. Then if the first one to be 4, the fourth is the second one to be 3. Then if the first one to be 5, second one to be 2. And the first one is 6, and the second one is 1. Right. We could see this later 3 just switch the first 3. So the 6 outcomes for 2, the face value of 2 dice adds up to be 7. So what is the probability? So number of outcomes in the sum to be 7 is 6. Number of the outcomes in the sample space, 36. So 6 over 36. 6 over 36 you can simplify, which is 1 over 6. Let's see example B. If 3 balls, now we have 3, are randomly drawn from a ball containing 6 white, 5 black, what is the probability that one of the balls is white? So 1 is white, and the other 2 black. So what is the probability to have when we take 1 out, is white. We have 6 white, 5 black. So what is our sample space? 11, right? We have 11 of them. Or what is the probability of getting white? Getting white is 1 over 6. What's the probability of getting black? 1 over 5, right? That's to see each event. So let's see the solution. The solution is quite long. So when we draw 3 balls from the 11 ones, so if we regard the balls being distinguishable and the order in which they are selected are being relevant, then the sample space consists of 11 times 10 times 9, 990 outcomes. So the possible ways of getting 3, 1 is white, 2 are black. Then the 6, 5 times 5 times 4, because draw the first one, second one, and third one, the 120 possible ways. If the first, which in the first ball selected is white and the other 2 are blacks, then if the, so this is for the first one, right? The first one is white, the other 2 are black. Then we have the other way. If the first is black, the second one is white, and the third one is black. So we would have this, because we have 5 black ones, 6 white ones, And then one black one is already out. We have 4 left. So that this many outcomes. Or if the first 2 are black, right? First one is black, 5 of them. One is out, 4 of them. And a white one with 6 of them. So assuming randomly drawn means each outcome in the sample space is equally likely to occur. So we see the probability is, so drawing one black, one white, and another black is this many. One white, the first one is white, the second one is black, the third one is black, that's this many. Then the first one is, the first 2 are black, the third one is white, and this many. It happens that all those numbers are the same because we have all these 3 numbers, but each one represents different outcomes. So add this up, 360. What's the total sample space? Total sample space, right? Join the first one, we have 11 ways. Join the second one, we have 10 possible choices. Join the third one, we have 9 choices. So the total sample space is 910. So 360 divided by 990, simplified to be 4 over 11. So this is one way to consider the desired probability. Well, let's see another one. So this problem could also have been solved by regarding the outcome of experiment as the unordered set of joint balls. From this point of view, there are 11, choose 3 of them, right? So out of 11, we choose 3. That's a sample space. That's the total possible outcomes, right? So out of 11 balls, we just choose 3 of them. How many ways? That 165 ways. If you take this one as sample space, then we need to think our event. So this is our sample space now. Now, each set of 3 balls corresponding to 3 factorial. Outcomes when the order of the selection is noted as a result. If all outcomes are assumed equally likely when the order of selection is noted, then it follows that they remain equally likely when the outcome is taken to be unordered set of selected balls. Hence, using the latter representation of experiment, we see that the desired probability is out of 6, choose 1, because we have 6 white ones, 6 white balls. We just choose 1 of them. How many ways of doing this? Then out of 5 black ones, choose 2. How many ways of doing this? By counting principle, we multiply them, right? This is how many ways to have 1 white ball and 2 black balls. So that's the event. So we're considering the event of this. So that's the event. Then this event divided by the sample space, 165, will also get a 4 out of 11. So this is a great example. This example is saying, you know, under application, right? So we have an application. And the sample space and the event is relevant. It depends how we perceive the sample space. But the event is relevant to the sample space we perceive. So one way, we could do this way, right? Then in this way, we have 990 possible outcomes in the sample space. Or we can think this way. In this way, we have 165 outcomes in the sample space. But the event has to be relevant to this sample space, this event. And this event has to be relevant to this sample space. All right. So we have to be consistent in considering the situation of probability in the same realm Anyone has any questions? Okay, this is talking about the general case. Let's see example 5C. A committee of 5 is to be selected from a group of 6 men and 9 women. If the selection is made randomly, what is the probability that the committee consists of 3 men and 2 women? Well, we need to choose the 5 and the 3 are men. How many men we have? 6. So out of 6, we want to choose 3. And out of 9 women, we want to choose 2. So by counting principle, we could just multiply. Those are our events, right? So out of 6 men, we want to choose 3. Out of 9 women, we want to choose 2. Then how many choices for having 3 men and 2 women? We multiply those 2 by counting principle. What is our sample space? Well, sample space, how many? We have 6 plus 9, we have 15. Out of 15, how many we want to choose? We want to choose 5. So sample space is a 15, choose 5. So we do the calculation, in the end, we get this number. Okay. If you want, right, if you want to practice, you can consider this way. You can also consider this way, all right? For 5 people, you choose the first one to be woman, blah, blah, all right? It lists the situations. That's a much long way. So this is very lean. Out of 6 men, we choose 3. Out of 9 women, choose 2. How many ways? Choose 3 men plus 2 women. We'll multiply them. Then, what's the sample space? 6 men plus 9 women, 15 of them. Out of 15, how many want to choose? We want to choose 5 of them. Let's say 5D. Now, N contains n balls, one of which is special. If k of these balls are withdrawn one at a time, with each selection being equally likely to be any of the balls that remain at the time, what is the probability that the special ball is chosen? We only have one of these special ones. What is the probability that the special one is chosen? Because we want to choose k of them. Okay. We want to choose k of them. So we have n balls. We want to choose k of them. What is the sample space? The sample space is out of n, choose k. Right? And we want a special. So what's our event? Our event is the special ball present, being chosen. So how many special balls do we have? There's only one. So that's why we have out of 1, choose 1, right? Because this is our event. We only consider the special one is chosen. Well, how many special ones we have? We only have 1. So out of 1, choose 1. Then 1 is choosing how many? So n minus 1 many. But we want to choose k of them, but 1 is already out. So out of n minus 1, we want to choose k of 1 of them. So we do the calculation, that's just k over n. Right. So the calculation is ignored. Anyone has any questions? Well, the bottom shows you another way of obtaining this one, but I don't want to go over there. I think this is the best way to to think about the probability, all right? Let's see example 5e. Suppose we have n plus m balls, of which n are red and m are blue. So that's pay attention to those numbers. Total we have n plus m balls, n are red, m are blue, are arranged in a linear order in such a way that all n plus m factorial possible orderings are equally likely. Because we're putting in linear order. Or what is that? Permutation. A permutation. So how many ways to permute n plus m things? Well, that's n plus m factorial. Possible orderings are equally likely. Okay, if we record the result of this experiment by listing only the colors of successive balls, show that all the possible results remain equally likely. Wow. Okay, so let's see how to do that. Consider any one of the n plus m factorial possible orderings, and note that any permutation of the red balls among themselves and of the blue balls among themselves do not change the sequence of colors. As a result, every ordering of coloring corresponds to n factorial, because we have n many red, m factorial, n many of blue, different orderings of n plus m balls. So every ordering of the colors have probability of n factorial multiplied by m factorial, because n factorial is many ways to order the red balls. M factorial is m ways to, we could see order or just permute. I like to use the word permute. Permute m blue balls. And over how many we have in total? N plus m factorial. Right? N plus m factorial means we're treating these red balls and blue balls are different. Yeah, how many ways of, put them on a line, how permute them? That's n plus m factorial. So this, the red ones together, the blue ones together. Okay, given an example, suppose there are two red balls and two blue ones. And we call R1, R2 for red, B1, B2 for blue. There are 4 factorial possible outcomes in total, right? But 2 factorial times 2 factorial ordinance in color combination. So for instance, the following ordinances. So we could have red one, blue one, red one, blue one, red one, blue one, red one, blue one, but with a different one. So again, we name each, even the same color, we will name each of the same color differently. So that's why we have these 4 different kinds of permutations, right? Permutations. So therefore, each of the possible ordering of the color has probability of 4 over 24, because of 4 factorial, right? If we put them, if we permute 4 things, we have 4 factorial, 4 times 3 times 2, which is 24. Then we have 4 over 24, which is 1 over 6. Right? Where did we get 4? 2 factorial times 2 factorial. So this is 2 factorial times 2 factorial divided by 4 factorial, which is 4 over 24. So this is just to show one example of this. Because again, this is a permutation, and also we treat each one, even they have same color, differently. Let's see this example. A poker hand consists of 5 cards. If the cards have distinct consecutive values and are not all of the same suit. Okay, by the way, the cards were 4 suits, and each suit has 13 numbers. Right. So we see that the hand is a straight. So a straight hand. A straight hand means distinct consecutive values like 1, 2, 3, 4, 5, or 2, 3, 4, 5, 6, or 3, 4, 5, 6, 7 consecutive and different, right? No two cards are the same suit or same number. And not all of the same suit that we see the hand is straight, so straight, which means the numbers are consecutive. For instance, a hand consisting of 5 of spades, 6 of spades, 7 of spades, 8 of spades, and 9 of hearts is a straight. The same suit, same suit. So what is the probability that a 1 is dealt a straight? All right. So 52 cards, because we have four suits, and each suit has 13 cards. So 4 times 13, that's 52 cards in total. So we start by assuming that out of 52, we choose 5, because one hand is 5 cards. So that's the sample space. Possible poker hands are equally likely. Then to determine the number of outcomes that are straights, let us first determine the number of possible outcomes for which the poker hand consists of ace, 2, 3, 4, 5. So ace is the letter A. Usually we treat it as 1. All right, usually treat it as 1. So ace, 2, 3, 4, 5. Right. So the suits being irrelevant, we don't care which suit. We have 4 suits. Since the ace can be any one of the 4 possible aces, and similarly for the 2, 3, 4, 5, it follows that there are 4 raised by 5 outcomes, leading to exactly 1 ace, 2, 3, 4, 5, right? So consecutive hand of ace, 2, 3, 4, 5. Then how many outcomes? 4 raised by 5. Because we have 4 suits. Hence, since in 4 of these outcomes, all cards will be of the same suit. Or if that's the case, the hand is called a straight flush. Just a term for it. So it follows that the 4 raised by 5 minus 4, right? Because we only have one possibility. You know, if it's consecutive, 4 cards, and also the same suit. So 4 raised by 5 minus 4 hands that make up a straight of form ace, 2, 3, 4, and 5. Similarly, there are 4 raised by 5 minus 4 hands that make up a straight from 10, jack, queen, king, and ace. So how many of these possibilities we have from ace, 2, 3, 4, 5? Then we can have 2, 3, 4, 5, 6. Then 3, 4, 5, 6, 7. So on and so forth. How many ways? You can count the 10 ways. The 10 ways. Because the last one is 10. 10, jack, queen, king, ace. End up with ace. So from ace we're treating as 1. So how do we count? From 1 to 10, how do we count? We do 10 minus 1 plus 1. 10 minus 1 plus 1. If we want to count from 10 to 20, we want to see how many numbers there. We do 20 minus 10 plus 1. Okay, we always add 1 back. So that's why it's 10. So ace we're treating as 1, 10, 10 minus 1 plus 1, that's 10. So 10 different hands. 10 of different consecutive hands. So 10 multiplied by 4 raised by 5 minus 4 hands that are straights. Then it follows that. So the probability we're interested in is this one. And the sample space out of 52 cards, choose 5 of them. So it's about this one. Negative 0.4%. All right, Ayat, okay. Yes, it's about that. 0.039 or 0.04. Yeah. Okay, anyone has any questions about this? Because I know some people, you know, never play cards before. I had students who never play, who doesn't even know the cards, poker cards. All right, let's see example 5G. Let's see how many examples. We may not be able to go over all the examples. Today, then we could go next class. Let's see, 5. Let's see this example. A 5-card poker hand is said to be a full house if it consists of 3 cards of the same denomination, which means the same suits. So 3 cards of the same suit and the 2 other cards of the same denomination, of course, different from the first denomination. That's okay. I guess it is a full house. I'm not quite sure, but I'm thinking a full house means 3 cards in the same suit, right? Denomination. And 2 full house. Well, same number consists of 3 cards of the same denomination and 2 other cards of the same denomination. What does denomination mean? Means suits or means number? Anyone knows? 3 of the same value. Oh, same value. Okay, thank you. Same number. All right, denomination. So which means 3 cards of the same number and the 2 other cards are the other same number, are the other number. So a full house is a 3 of one kind plus a pair. Oh, okay. What is the probability that a 1 is dealt a full house? All right. The sample space is still 52, choose 5 cards. All right. Then each, remember we have 4 suits. So that means we have 4 numbers. We have 4 of the same numbers because each suit goes from ace, it has 13 numbers from ace to, you know, up to 10, jack, or queen, right? And king. So they have the same kinds of denomination. That's why maybe they call denomination not number, because, you know, jack, queen, king is not a number, and the ace is not a number. So that's why they call denomination. Okay. So each suit has 13 of those. So that means in 52 cards, we have 4 of the same denomination. All right. We have 4 tens, 4 aces, 4 twos, 4 threes, 4 fours, so on and so forth. All right. So let's see. We first know that these are out of 4 cards, choose 2, right? We have 4 of the same denomination. We want to choose 2 of them. Then 4 of the same denomination, we want to choose 3 of them. By counting principle, we multiply those 2. We multiply those 2. But how many? Okay. There are 13 different choices, right? Because those 2 cards, those 3 cards, could be any one of those 13 denominations. So assume the first one. So the first one will be 13 choices, right? Will be 13 choices, and the second one will be 12 choices, because we want the two different, because 3 are the same denomination and 2 are the same denomination, right? And the plus together is 5, so they cannot be the same denomination. So once one denomination is chosen, then we only left 12 denominations, right? So this might be 3 of the same denomination or 2 of the same denomination, or maybe this one. So that's why we have 13 multiplied by 12, multiplied by out of any 4, choose 2, out of any other 4, choose 3. Divided by the whole sample space is out of 52, choose 5. Anyone has any questions? Okay, let's see. H. In the game of bridge, any one of you play this? You know, those games are my generation games. You know, we play poker, we play bridge. The entire deck of 52 cards is dealt out to 4 players. What is the probability that A, one of the players receive all 13 spades? B, the 4 suits are spades, hearts, clubs, and diamonds. Okay, so spades is one of the 4 suits. So each player receive 1 ace. So 4 players, each one receive 1 ace. There are 4 aces in one deck. So the first one means, you know, one person gets one of the suit, because each suit has 13 spades. Spades has 13 denomination. Okay, let's say 8. Letting EI be the event that a hand I has all 13 spades. Then probability of EI equals to 1 over out of 52, choose 13 cards. Out of 52, choose 13 cards. But because out of 52, choose 13 cards. Because 52, you know, we can choose any of the 13 cards. That's a sample space of having 13 cards, right? There's a sample space for having 13 cards. And what is the probability? What is the outcomes? Get all 13 spades. This is 1. Right? This is 1 suit is a spade, and a spade has 13 cards. So this is 1. So that's why probability of that is 1 out of 52, choose 13. And but, so I represents 1, 2, 3, 4. It could be even 1, even 2, even 3, even 4, because one of the players, right? One of the players, and we have 4 players. We have 4 players. It could be player 1, player 2, player 3, player 4. Because the events, the 4, E1, E2, E3, E4 are mutually exclusive. Because one player gets the space, the second one cannot, right? The second one cannot, so they're mutually exclusive. So the probability one of the hands is dealt all 13 spades is probability of union of all those 4 players, and it's just probability of 1 multiplied by 4, right? So it's just probability, so adds up all those 4s. So I goes from 1 to 4, probability of this EI. Remember what is the probability of EI is this, right? So 4 times. So basically is 4 times 1 over this, or 4 divided by this, 4 times 1 over this, which is, if you calculate, you get this number, very small number. So very small chance when you play a bridge, you know, you get 13 cards all in 1 suit. Let's see B. Each player receive 1 ace. Each player receive, so that we use a multinomial. Let the outcome of experiment be the set of 13 cards of each of the player 1, 2, 3, 4 to determine the number of outcomes each one of the distinct players receive exactly 1 ace. Put aside the aces and note that there are this many possible divisions of the other 48 cards when each player is to receive 12. Because we imagine each one receive 1 ace. 52 minus 4 aces, the 48 cards left. And each one's supposed to get 13, but they get 1 ace already, so that 12 cards left. So how many ways of distributing that? That's this multinomial. Because there are 4 factorial ways of dividing the 4 aces, right? So that each player receives 1. We see that the number of possible outcomes in which each player receives exactly 1 ace is 4 factorial multiplied by this multinomial. That's how many ways. And what is the sample space? The sample space is out of 52, distribute 13 to the first one, distribute 13 to the second one, to the third one, to the fourth one. This is beautiful, isn't it? So 4 factorial permutes the aces, to each one of the players, right? The 4 players, each one has 4 possibilities, getting 4, one of the 4 aces, because of 4 different suits, right? So each player may have, one of the 4. So that's a 4 permutation, right? So 4 factorial, that's permutation, so 4 factorial. Then multiply by how many ways to get to the rest of the 12 cards. So out of 48, the multinomial. And divided by, out of 52, distribute 13 cards each. That's 0.1055, right? Almost 11%. So that's a big, considerable chance. Any questions for this one? All right, so you know what? Let's finish here. So we're going to keep talking on Thursday, talking about the rest of the examples. I think this chapter is very interesting. All right. Example 5i. Let me make a note so I won't forget. 5i. All right, anyone has any questions? Keep your good work, all right? Keep your good work and pick some interesting questions to present next class. All right, I'll stop recording.